Hello. Good morning to all. Good morning. Good morning. Very good morning. So let us see.
Good morning, sir.
Today's very good morning. We'll wait for again 1 minute. Let other students join. Try to join before 8:30 so that we can start our lecture within time. So last time we were talking about that is the elimination reaction, right? Elimination reaction, and we have seen what is meant by elimination reaction, definition, types of elimination reaction, 1-1, 1-2, 1-3, 1-4, 1-5, and 1-6 elimination reaction. In that 1-2 elimination is important, and this 1-2 elimination reaction also can be explained by 3 mechanism: E1 mechanism, E2 mechanism, and E1CB mechanism. And now we are discussing about the E2 mechanism. In E2 mechanism, we have seen that bond breaking and bond forming process takes place simultaneously, and there is a formation of corresponding alkene. So it is a one-step process. We have also explained evidence for the mechanism. We have given the evidence, and we have seen that the elimination takes place by the Saytzeff rule. So we have seen what is this Saytzeff rule. Saytzeff rule means when there is an elimination, then elimination takes place in such a way that there is a formation of corresponding alkene in which there is a more alkyl group directly attached to the doubly bonded carbon atom. Means highly alkyl substituted alkene is formed as a major product. So last time we have discussed the Saytzeff rule. So let us see today justification for the Saytzeff rule. Then the justification can be explained by using stability of alkene and energy of activation. So let us see justification for the Saytzeff rule. So we have seen already what is meant by Saytzeff rule. What is meant by Saytzeff rule or Saytzeff elimination? In Saytzeff elimination, we have seen that in suppose there is a such type of substrate, there is a carbon-carbon double bond, and here is suppose in particular, if you take example, there is a CH3 or you can take R. Here is a hydrogen. Here is also hydrogen. Here is also hydrogen. Here you can take one more R group, and in this case we can take here CS2 and H means CS3. And here is a halogen. Halogen you can take there is a Br. So the carbon atom which is directly attached to the functional group is called as alpha carbon atom, and the carbon atom which is directly attached to the alpha carbon is called as a beta carbon atom. So there is the presence of two type of beta hydrogen. So here is this hydrogen is a beta, right? and this hydrogen is a beta dash, beta dash. So this is also directly attached to alpha, so it's also called as a beta. So I label it as a beta dash. So these your beta hydrogen and beta dash hydrogen. So here, if there is a E2 elimination, if there is a E2 elimination, then bond breaking, bond forming process takes place simultaneously. The reaction takes place in the presence base, for example, Na plus O minus E2H5 means oxide. The reaction follows by E2 mechanism. So bond breaking, bond forming process takes place simultaneously. So here, what happens? The bond between C and Br break. This will break. Why? Because Br is more electronegative as compared to carbon. So this sigma bond on the Br negative and C positive. Carbon positive. Where there is a tail of the arrow, here you get the positive charge. And where there is a tail of the arrow, you get a negative charge. Why? Because the shear electron pair between the C alpha and Br will open on the Br. So Br is C positive. So carbon having the positive, there is a generation of positive charge. So you have to neutralize this positive. So this sigma bond will shift here. This sigma bond shift here, and this base abstract this proton. So here you are having a base C2H5O minus. So this base will abstract proton, and there is a formation of corresponding ethyl alcohol. So there is a formation of a such type of compound. So if there is an abstraction of a beta hydrogen, then you are getting such type of compound. There is a CS3, here is a C, here is a H, here is a formation of a carbon-carbon double bond between the C alpha and C beta. Here is a, in this case, there is a H, right? So there is a H. So here there is a H, and here there is a CH3. So you get compound number 1, that is called as a 1 is alpha carbon, and there is a beta carbon. So there is a formation of bond between the alpha and beta. 1, 2, 4. So it is 2. There is a formation of 2 butane. Similarly, also this sigma may also break. So in this case also, the beta hydrogen may also break. So this sigma may also break, and there is a formation of a corresponding alkene. So you can get in this case CH3, CH2, get compound number 2, and this compound number 2, here is a alpha carbon atom, and here is a beta carbon. Right? There is a abstraction of a beta hydrogen. So you get 1 butane. So this elimination is governed by the Saytzeff rule. What Saytzeff rule tells that the elimination takes in such a way that there is a option of highly substituted as a major product, right? In this case, you are 2 butane and 1 butane. In here is a R, right? Here is a R. In this case, there are the 2 alkyl group. We can say here this methyl group and this methyl group is a direct attached. So I can label as here is a 1 R. There is a 1 R directly attached, and other R is this one. So the 2 alkyl group directly attached to the doubly bonded carbon atom. So it is a dialkyl substituted alkene. Right? And here only 1 R group is directly attached. Ethyl group is directly attached. So it is a monoalkyl. Monoalkyl means only 1 alkyl group is directly attached. Saytzeff rule tells us that there is a formation of a highly alkyl substituted alkene, means there are the more number of the alkyl group directly attached. So in this case, here it is a di and here is a mono, means if there is a formation of a more number of alkyl group on the doubly bonded carbon atom, then it's a major compound, and here it is a minor compound. So it is a major and a minor compound, right? So there is a formation of a major and a minor compound. Now here you have seen the formation of major and a minor compound by the Saytzeff rule. So it is called as the Saytzeff rule. Now question arises, why this number 1, compound number 1, that is a 2-butane is a major, and number 2, that is a 1-butane is a minor. So you have to give justification for the Saytzeff rule. So you have to give, that is the justification for the Saytzeff rule. So let us see justification for the Saytzeff rule. So this justification we can give by giving an example. One, we can see the stability of alkene. Stability of alkene. So you know, every species want to attain stability, or every species want to attain stability. In this case, in this alkyl halide 1, 2, 3, 4, I2 there is a bromine. So 2 bromo. Here is a 2 bromo. And how many carbons are there? 1, 2, 3, 4. 4 means butane. So in this case, bromobutane, there is a formation of 2 butane and a 1 butane. So you know, if this undergo elimination, the elimination takes place in such a way that there is a formation of a more stable compound. So you have to check whether the stability of 2 butane is more or 1 butane is more. So we can explain the formation of a major compound by using a stability of a alkene. More the stable alkene, more is the compound, means more is the major product, right? More is the major product. So the stability of this alkene can be explained by using heat of hydrogenation. We can explain by heat of hydrogenation. Heat of hydrogenation. So what is the mean by heat of hydrogenation? Heat of hydrogenation means when this alkene undergo hydrogenation. Hydrogenation means there is addition of hydrogen. So it will convert into corresponding alkene. So when alkene undergo hydrogenation, the amount of heat evolved is called as a heat of hydrogenation. So lower the heat of hydrogenation, more is the stability. Lower the heat of hydrogenation, more is the stability. So in this case, if the alkene is having a lower heat of hydrogenation, then here if lower heat of hydrogenation, then the alkene will be stable, right? Alkene will be more stable. So here you have to see the experimental data for this compound. So here we'll take a direct experimental data of corresponding different type of alkene. So let us see the stability of alkene depending upon heat of hydrogenation. Heat of hydrogenation. So here the heat of hydrogenation we can take like this one. Number 1, we can take example alkene. Alkene, book to book, sometimes you may find different data. So we should know which have the lower and which have the higher, right? So here we'll take some example. Here is the alkene. Then you have to find out the substitution pattern, whether what is the order of substitution, whether it is a mono or di substitution, and you have to find out the heat of hydrogenation. So here is a order of substitution. Order of substitution. Order of substitution of alkene. And here is the heat of hydrogenation. Of hydrogenation. Number one, suppose if you take in this case simple example again, that is 1 butene CH3 CH2 CH double bond CH2. It is your 1 butene. Also we can take the next example, that's the 2 butene. Here is the CH3, then CH double bond CH and CH3. So this is the next example, 1 butene, then 2 butene. Here if you see the order of substitution, it is a mono substitution. It is a mono substitution. It is a mono substitution, right? It is a mono substitution because only one R group is directly attached to the doubly bonded carbon atom. Here look, in this case only one R group is directly attached to the doubly bonded carbon atom and remaining are the hydrogen atoms. So it is a mono. Here it is a di substitution. Di substitution. Why? Because here are the two alkyl group. One is this methyl group and other is this methyl group is directly attached. So it is a di substituted compound. Next example we can take, right? So here we'll take few example. If we take, it is a mono, it is a di. Again in this one we can see cis and trans, right? So we'll go for the, that is again another example, that is a tri-substituted compound. So we will not take other examples, only we'll compare with some of the alkene. Here is a CH3, here is the carbon-carbon double bond, and here is a CH3. So in this case, it is a tri-substituted. It is a tri-substituted alkene. Why tri? Because one R is this one, other R is this one, and third R is this one. So first is a mono, second is a di, and third is a tri-alkyl substituted. In this we can take also other example also. Just for comparison, I have taken this example. Now heat of hydrogenation. We have to find out the heat of hydrogenation. So in mono, experimentally it is found that the heat of hydrogenation of 1 butene is found to be 30.3 kilocalorie per mole. So for this one, 30.3 kilocalorie. And for di, again in this di, we can take cis and trans. We can take a cis and trans. So here in this one, if it is a cis, you are having a 28.6 kilocalorie, and if it is trans, it is a 27.6 kilocalorie. So it is for cis and it is for the trans. So this is for the cis alkene and this is for the trans alkene. The heat of hydrogen is the and it's 30.3, so it is a 0.3 kilocalorie. So in this case, the heat with this compound, mono and di, compare mono and di, we'll find that the heat of hydrogenation of a di is a 27 or 20, means less than the mono, less than the mono. The lower hydrogen, more is the stack. Here, how many carbons are there? 1, 2, 3, 4. 1, 2, 3, 4. You have compared 2. Compare this 2. Then you see that this cis and trans is having the lower heat of hydrogenation. If you compare two compounds, means lower heat of hydrogenation, more is the stability. So this compound means disubstituted compound is more stable as to mono. And again in the cis and trans, again you see that the trans alkene is found to be more stable than the cis compound. And you know why are more stable? Why? Because the group, they are on the opposite side. The R group are on the opposite side. So there is a steric hindrance, and you will see that it is found to be more stable. Similarly, we can compare this. How many carbons are there? 1, 2, 3, 4, 5. So you can take now. Similarly, in this, we take another example. In the case number 2, suppose if I take here try of this one, then you can take disubstituted, that is the CH2. Then there is a formation of a carbon double bond. Here is a CH3, and here is a CH2 and CH3. So there are two alkyl group, right? So it is a di. And if you see the heat of hydrogenation for the di, it is found to be 28. So I have written the wrong. It is a 26.7. It is a 26.7. It is a 26.7. 26.7. And if you see this die, you will see that the heat of hydrogenation for this one 28.5. 28.5. So here from this experimental data, you may say that lower the heat of hydrogenation, more is the stability. That's why the alkene formed by using the Saytzeff rule, it gives a more stable alkene. That's why the Saytzeff rule gives highly alkyl substituted alkene. So in general, we can now make a statement that the tetra is a more stable. Means I can write here carbon, here carbon double bond, here is R, here is R, here is also R, here is also R, means tetra, right? It is a tetra. So tetraalkene is a more stable than the tri. Tri, here I can write R2C double bond C H and R. It is a tri. Means there are three alkyl group, 1, 2, 3. Then di. In di again there is a cis and trans. So here we will not see cis and trans. R, CH double bond CH and R. It is a di. Di is less as compared to tri. And similarly, there is a mono and ethylene. Here is R. Here is the CH double bond CH2. It is a mono, and here is a ethylene. CH2 double bond CH2. So this explains that lower the heat of hydrogenation, more is the stability. More is the stability, right? So this is the Saytzeff rule. And this is the Saytzeff rule we have seen. In this way, we can explain the stability of any alkene. So we have to check the heat of hydrogenation. We have to check the heat of hydrogenation. And depending upon that one, we have to check the stability, right? Now, next justification we can give by energy of activation. Energy of activation. Energy of activation. You know energy of activation. What is meant by energy of activation? EA. Anyone can tell what is the energy of activation? Yes. Anyone? Srikant, what is the energy of activation? जल्दी से बोलो.
Yes, sir.
हाँ, what is the energy of activation? Ankita, what is the energy of activation? We have seen also in the nucleophilic substitution reaction. What is meant by energy of activation? Anyone can tell? Yes. Supriya Chaudhary, what is the energy of activation? Yes.
It is the minimum amount of energy required by the reactant to react and form the product or transition state.
Very good, right? So, what is the energy of activation? Energy of activation means it is the minimum amount of energy required by the reactant to pass over the transition state is called as the energy of activation. Right? So, here we see the in reaction. You have seen that like this one, and in this there is a hydrogen. This carbon is called carbon as a beta, right? Now, in this case, if you see the of base form a bond with this one. So this sigma bond will open on X negative positive. This will shift here, formation of bond, and this base abstract on. So the bond breaking and bond forming process takes place simultaneously. Right? So we are having a formation of a transition state. Formation of transition state. So in the transition state, what happens? The bond between C alpha and C beta. These are C alpha and C beta. So here the bond between the C alpha and X undergo breaking. The bond between the C alpha and C beta undergo forming. At the same time, the bond between C alpha and undergo forming, and you are getting a such type of here is a H and here is a X, right? So this bond break, this bond form, this bond break. At the same time, the bond between this H and this B undergo form, right? So there is a formation of a such type of a transition state. Formation of such type of transition state. We have seen it is a slow step RDS step. Slow step RDS step. And further in the fast step, this sigma bond break completely. Formation of negative C becomes positive. This will shift formation of a double bond, and this will form a complete bond with hydrogen, and there is a formation of a corresponding alkene. So here is a C, here is a formation of a carbon-carbon double bond, the remaining part as it is, right? So it is your alpha carbon, it is your beta carbon atom. So this is the mechanism of the reaction. So this is your substrate, this is your substrate, this is your transition state, and this is the product that is a form, and that is the alkene. Now question arises, which will have the lower energy of activation? Lower energy of activation. You know, suppose I take example in this case, just I will make a change in the same example. Here is carbon, here is I will not show in detail the transition state. So you are having a, suppose there is a CH3, here is a H, and in this case here is also H, and here is your H, here is your suppose Cl, and here is a, again one more, that is the CH2. So same thing example you have taken. So what happened in this case, in the above, the bond between the C alpha beta and this is your beta dash, right? So this sigma bond will open, this will shift here, or this may shift here, and there is a formation of a corresponding transition state, and I write direct product, that is a CS3 C, here is a H, here is a double bond C, here is a H, and here is a CH3. You get compound number 1, and you may also get compound number 2. That you have learned this reaction already. So there is no need to go for the mechanism. You can go for the mechanism. Just you can replace this R, this valency by this one, you get the mechanism. Now question arises, there's a formation of compound number 1 and compound number 2. So which have the lower energy of activation? You have to check, right? Which have the lower energy of activation. So here we can write, this is your, suppose x-axis and y-axis. This is your x-axis and this is your y-axis. These are the reaction coordinates. This is the reaction coordinate. And this is the potential energy, right? Now here, suppose this is the energy of the reactant. This is the energy of the reactant. As reaction start, then there is a formation of transition state, and further it will break down and the formation of corresponding product. So here the energy of this one is a reactant, and reactants are what? In this case, the reactants are, that is CH3, then CH2, CHBr, and CH3 plus base. We can take base anything, means here you can take ethoxide or you can take a base. As reaction start, suppose this is the energy of the reactant. As reaction start, there is a formation of a transition state, and further it will give the product, and the products are the 1 and 2. Now here we have to check the formation of product. It is seen that there's a, if there's a formation of a compound number 1, here it is a disubstituted. Right? So its stability is more. It is seen that the energy required for the formation of a transition state is, suppose we take, this is the energy of the transition state for this compound. So here we write the compound number 1, and here is a compound number 1, that is a CH3, CH, double bond, CH, and CH3. So this is the energy of the compound number 1. It is seen that if suppose there is a formation of compound number 2, then in this case the energy for this one is more as compared to previous one. So this is the energy of the reactant. As reaction start, it is seen that there is it require more energy to pass over the transition state, and further it will break down, and again there's a formation of a compound, and here you get a compound, right? And the energy of this one again somewhat higher than the one butene. So there is two butene. So here is a one butene, and you get compound number 2. The energy required to the pass over the transition state. Here is a transition state. The energy difference between transition state and the energy of the reactant is called as energy of activation, EA, energy of activation, EA, right? And in the next case, here energy of activation for the again the one butene, so it is EA dash. We can say EA dash, EA dash. So the transition state of formation of compound number 2 is a more. It have the more energy, it have the higher energy of activation as compared to the second compound. That is the first compound. There is a 2 butene. So lower the energy of activation, in that case more is the Saytzeff product. So from this one we can say that the this compound, if you see this compound, if it undergo elimination reaction, in that case the compound form, right? Here the compound form, that is the first is a major, right? The first is a major and second is the minor. So why it is a major? Because the energy of activation is lower as compared to this EA dash. EA dash is the more. So here the EA dash is a more as compared to EA, right? That's why the first compound is a major as compared to the second compound. So this is the justification for the Saytzeff rule. One more again evidence we can give in this Saytzeff elimination, and we can give also one more evidence for the Saytzeff elimination. Suppose you are having a such type of bond. Here is the by using the resonance effect. By using the resonance effect, suppose if it stabilize corresponding alkene, then it favor the Saytzeff elimination. For example, suppose you're having a such type of starting compound, pi bond, benzene nucleus. There is a CH. Here is the H. Only I have written here R is equal to pH. A remaining part as it is. Here is a suppose Br, and here is a CH3, right? Only I have make a change in R. I have put here pH, phenyl. Further, it undergo alcoholic, the reaction with alcoholic KOH. So of course here this is also alpha carbon, this is your beta carbon, this is your beta dash carbon. So in this case the elimination takes place, and this sigma bond open on the Br negative, C positive. So we can replace this sigma bond, you can also replace this sigma bond, and you are getting two compound, that is pH. Here is a CH, a double bond CH and CH3, right? And also you can get corresponding compound, that is a pH, CH2, CH double bond CH2. So you can get compound number 1 and compound number 2, right? Of course it is a di substituted, right? So because there are R group, of course you can say that one is a major as compared to second, but also if structure permit, then also if it undergo resonance, then also it use the more that is the elimination product, that is the Saytzeff elimination. So in number one, you will see that there is the presence of a benzene. Right? There is the presence of benzene. There is a pi bond. Here is a pi bond. Here is a pi bond, and here is a CH double bond, CH and CH3. Here is the compound number one. This pi bond is in the conjugation with this carbon-carbon double bond. So if structure permit, it undergo that is the resonance, and it use more stabilization. So this carbon open on the carbon, this pi bond open on the carbon, C becomes negative, C becomes positive. So this pi bond will shift on the sigma bond, formation of a double bond, and you can get the next resonating structure. Here you are having a such type of resonating structure. So here is the pi bond, here is the pi bond. So this is shift here, means this carbon carries a positive charge. There is a formation of a carbon-carbon double bond. Here is a CH and here is a CH negative and a CH3. Further, it also undergo resonance. So here the sigma, this pi bond will shift on this sigma bond. You can get formation of pi bond, and this carbon carries a positive charge. So here you are having a next resonating structure. Here is a benzene nucleus, right? So this carbon carries a positive charge. This carbon carries positive charge. There is a formation of pi bond. Here there is a formation. Look here. This is shift here. Means this carbon carries positive. This pi bond as it is, right? And here there is a formation of pi bond. Here is the CH. Here is the CH negative, and here is the CH3. Similarly, you can write another example, etc. Right? So the compound number one is further stabilized by the resonance, right? So if the compound form is the further stabilized by the resonance, then it also gives a corresponding more stable compound. Why second compound is not formed major? Because in second compound, the pH nucleus is not in the conjugation with the carbon-carbon double bond. So these are the two evidences for the justification of the Saytzeff rule. So we have seen two evidences. One is the Saytzeff rule, that is the stability of alkene, and second is the lower energy of activation, and third is the resonance effect. So in this one, if you have any doubt, you may ask. So here, what we have learned, right? We have learned in this one, we know what is meant by Saytzeff rule. The elimination takes place in such a way that there is a formation of a highly alkyl substituted alkene as a major compound. We have to give the justification of the Saytzeff rule. The justification can be given by the 2 point stability of alkene and the lower of energy of activation. So here we have seen Saytzeff rule, and you have to give that is the justification. In this case, the 2-bromobutane will undergo base. There is a formation of compound number 1 and compound number 2. You know the compound number 1, that is the 2-butane is a major and 1-butane is a minor. Why 2-butane is a major? Because we can explain the formation of a major compound 1 by A, that is the stability of a alkene. More the stable alkene, more is the formation of that compound. So the stability of alkene can be explained by using the heat of that is the hydrogenation. And so here the more the heat of here lower the heat of hydrogenation, and more is the stability. So here in this case, lower the heat of hydrogenation, more is the stability. And here we have taken few example of alkene, that is first compound, it is a monosubstituted, here is a disubstituted, it is a trisubstituted. This monosubstituted having a heat of hydrogenation. Experimentally it is found that it is a 30.3 kilocalorie per mole. You know what is the mean by heat of hydrogenation? Heat of hydrogenation means the amount of heat evolved when saturation, means that pi convert into the single bond, and the amount of heat evolved is called as a heat of hydrogenation. Lower the heat of hydrogenation, more is the stability. And here you have seen di is having 28.6 or 27.7. Again, the trans is the more stable than the cis. In case of example and di, the tri is having a 26.7 kilocalorie per mole energy. In the sequence steady is more stable than the tri, then the mo, and then the methyl. So next example, we have seen the justification by using the energy of activation. Lower the energy of activation, more is the stability. And then we have seen how it undergo the formation of compound, and so you have seen the resonance, how it stabilizes compound number one. So here compound number one, the region is in the conjugation with this bond. That's why it is also further stabilized by the resonance. In this way, we have seen the justification for the step rule. Right? Any doubt you may ask. इसके अंदर आपको कोई डाउट है तो आप पूछ सकते हो. Yes, Tushar. If you have any doubt, you may ask.
No doubt, sir.
No doubt. Yes, Sakshi Chavan. Any doubt?
Yes, sir.
Right? Are you getting? आपको समझ में आ रहा है?
Yes, sir.
Rohit. And are you getting?
Yes, sir.
Right? Yusti.
Yes, sir.
In class, every time also you have to read at your home. And when you read at home, then you can understand those concepts very, very easily. I think we should stop here.
Thank you, sir.
So, now we can leave the meeting and you can join the next lecture.
Thank you, sir.
Thank all. Thanks to all. You can leave meeting. Thanks to all. You can leave meeting.